built to sink. The loss of Titan in early June prompted me as a designer and a builder of ships to write a paper for laymen defining the causes of the failure. My basic source of information is whatever was given to the media. It's a vessel where I would not even board the vessel at sea and let anybody close the hatch, a hatch which cannot be controlled from inside, which we cannot be opened. The craft, any engineering structure which is built is regulated by rules and regulations of the country. The design, the construction, the materials, the quality control, the personnel, the training of the personnel, the maintenance, the navigation at sea, the safety of life at sea, the certification of all the components and the vessel itself is carried out by government regulations. In the United States, there are organizations which control all marine structures. The first one is International Maritime Organization. This is a conglomerate of 167 countries, which also incorporates safety of life at sea. Then we have the American Bureau of Shipping, the Department of Trade, the Product Designation Approval. Then we have the US codes, American Society for Testing of Materials, United States Coast Guard, the data analysis. For me, the failure was predictable. It was sure that one of these days this craft will sooner or later. We do not have the design analysis or the design calculations of the vessel. However, it can be assumed that finite element analysis were carried out. Von Mises and such equations were used to calculate the thickness or the load on the external part of the hull. The thing which strikes you when you look at the shape as displayed all over the news, they have selected a cylindrical vessel, and the material selected for the cylinder is carbon fiber. This is a very strong material known to mankind. It has anisotropic properties, which means that the properties vary in the three planes. As you know, in a space there are three planes, X, Y, and Z. The carbon fiber exhibits different properties. Engineers normally use this property to their benefit. The way is that if you pull the carbon thread, it is very strong. Let's have a look at a cylinder on which carbon thread is wound in a spiral manner with a zigzag pattern. When I pull the thread, it is strong. And when I pull it on the Y plane after the X, it is still strong. However, when you pull the thread upwards from one thread to the next one, it just lifts. The only bonding compound there is the epoxy resin, which means it has very little strength in the Z plane. Now, translating this into high load, low fatigue, the writing is on the wall. When the vessel goes down the water, the pressure compresses the hull. And as it comes up, the hull expands again. This movement is through the thickness, the 5-inch thick carbon fiber, which means after a certain number of cycles, it will delaminate, the layers will delaminate and the hull will leak. The carbon fiber is 5 inches thick. The ends are joined with dome-shaped titanium, and within the titanium there is a window in acrylic. Now let's look at these two dissimilar materials, the cylindrical carbon fiber and the titanium dome. The carbon fiber having anisotropic properties, whereas titanium has isotropic properties, which means it is the same strength in all the three planes. Just visualize the vessel again diving down and the hull shrinking by the external load of the water pressure. the properties are different. The carbon fiber and the dome will shrink in a different stress, which means there will be relative movement between the two, both when it's going down and when it's coming up. And the joint, which is already a high stress area, will eventually fail. Let me talk of a few of the design aspects which with my experience, the points. For example, when the hull was designed, there don't seem to be there any frames inside or outside. Whereas we all know that in normal structures, if you put framing, it delays the failure. And it also improves your diving depth. Why were frames not provided inside or outside? This is something, you don't leave that cylinder like that, because otherwise it collapses suddenly. All the small structures in composite which we have tested, it's a total collapse. Or even if you take a can and create vacuum, it's a total collapse. The moment you put frames in, you get a sinusoidal type of function. Now let's look at the through hull fittings. It has not been mentioned. There are penetrations in the pressure hull, like the cables, the hydraulic services, the control pipes, the controlling wires, all these pass through. There are special methods of making these openings, especially where the wire passes. If care is not taken, it walks into the hull and eventually leaks. I don't know how the hydraulics are controlled. What were the ballast release mechanism? How was that command passed on? Then one more very important thing. Before a vessel goes for a dive, a complete trim calculation is carried out. As per the Archimedes principle, the float, the weight of the vessel and the buoyancy, extra ballast is controlled carefully. Even the personnel who have to go in have to be weighed, the food, the equipment which they're carrying, everything is weighed. And in this craft, what I understand, the movement in water was generally through the thruster motors. Whereas in real underwater vehicles, they have a small trim tank for fine control, which means for a little bit of movement or for neutral buoyancy, you take out small amounts of water or take in small amounts of water in tanks located outside the pressure hull, known as the trim tanks. Looking at the hull, the outer hull, it's horrifying. These saddle supports are flimsy. Even the trolley of a normal automobile pulling a boat is stronger than the saddle supports shown. Of course, these saddle supports will be banging on the floor. If the submarine has a certain downward velocity when it's going down, it is going to hit the bottom. It has to be strong. It can also be used as a ballast, as it has been mentioned somewhere, but this consideration should have been done. The vessel's movement is controlled by thrusters, upward thrusters, forward thrusters, going down thrusters. If you look at them, they are flimsy. They are attached loosely outside. Somewhere down below, it could hit that vessel, the ship, or any obstruction. Why are these thrusters not properly protected? This is surprising. The only thing I can praise is the Kongsberg sonar. They are excellent manufacturers. I don't know which model is fitted over there, whether it is up to the mil spec or not. The other point in the design is, why is no position indicator installed on the vessel? There should be at least two of them, and transmitting their position continues to the mothership. Secondly, why there is no navigation mechanism? Total reliance on the mothership. There should be some equipment which tells you where the vessel itself is. The next point is that on the pressure hull in the carbon section and probably elsewhere, they have sensors which have lights which come on and off during the voyage. The non-destructive testing of the hull was not carried out anyway, but the behavior of these hull while diving and coming up could be recorded from these sensors, and they would give you a warning that a failure is about to occur. After every voyage, the recording should be analyzed and checked for the seriousness of the issue. I am surprised why this was not done. This is a basic requirement. Let me look at the outer casing. It is flimsy. It is not properly done. I will come to the services which are within the casing and the pressure hull. But looking outside, most of these things look like mail order. For example, the fenders are flimsy. Looking at the launch of the vessel from the pontoon, one could see a square threaded rod. Poor workmanship. Naked rod lying there. I don't know what the application was. However, one doesn't do this kind of a thing when you're dealing with such important craft. In one of the pictures, I saw a man using a wrench to tighten the boards. This was an ordinary torque. It was not a torque spanner. How is it that the nuts are being tightened without measuring this torque? This is unbelievable. Even the outer straps which are holding the skid, they look so flimsy. And I understand they're supposed to get dissolved. You don't wait for time. When the boat is going down with a certain velocity, you want to come up quickly. You want to lose buoyancy, add buoyancy very, very quickly. Straps should be, as I said, it is very important that the crew is trained. Everything has to be, shall I say, we should carry out reliability analysis for all the equipment. There should be duplication of the crew also. There should be backup systems. And to ensure that in the event of one item failing, the continuity is provided. This wasn't looked at. Only one man controlling the whole thing? What about the panic? What happens if there's a panic? What about the position indicator? What about the communication system, which had been failing regularly? Why there was no backup? There are so many other points which I could mention. This would make this video very long. In the end, I would like you to thank all of you who have watched.